questions do you have? No, we have to do it at the end so that you can go when you're done. Okay. So we got some stuff to do first. We'll always do quizzes at the end of the hour. All right. Well, let's talk about some new stuff. This is just going to extend on stuff that we've already done. We've already talked about net change. We've already talked about not net change. This particular section talks about average rate of change. Remind me again what net change means. Yeah, so it would be the difference between where you ended up and where you started, right? That's the net change. So let's look at this first problem here. We're asked for average rate of change. If we're just asking for net change in the population from 2008 to 2012, what would you do to find the net change in the population? Good. Yeah, you would just do the net change would be the population in 2012, right? Minus the population in 2008. We've done net change, right? Where you ended up, where you started. Do the difference between those two, that's net change. So in this case, you would have 6375 minus 4869. What is that? 1504? Nope, sorry, 06. If I did that right. That's what a calculator is for. But so that would be the net change in the population, right? How long did it take for that change to happen? How many years did it take for that change to happen? 4 years, right? So if you want average rate of change, what do you think you want to do with that 1506? Divided by 4, exactly. So your average rate of change will be your net change divided by basically the length of time, or the length of the interval. So you do the 1506 minus, or excuse me, not minus, divided by the 4. Say it again. 376.5. And if we want to interpret this in terms of units, the population is people and the time is years. So this would be an average rate of change of 376.5 people per year. Right? We have the number of people over number of years, so it'd be people per year as far as units go. So that's all we need to do for average rate of change of a function. We figure out how far you went, that's net change. We're going to divide it by how long it took, the length of the interval. So that's exactly what we did here. So it's just, like I said, it's just an extension of what we do for net change. So if you wanted the average rate of change between 2014 and 2018, what would you compute in this case? Vivian? Okay. And then we divide that by. So how many years are between those two? 4, yeah. You can actually think of it as 2018 minus 2014, right? The difference between those two things. So we divide it by 4 again. And what do we get there? Negative, what? Say it again.
Okay, so it'd be 13, what is it, 1367? And then what'd you say again for the number? 30? Okay. And again, our units here would be people per year. Any questions on how we're getting that? Again, we're just doing net change, so we're doing ending value minus starting value, and then dividing by how many years there are, divided by the length of that interval. Notice that in the first one, the rate of change is positive. In the second one, the rate of change is negative. So looking at the particular signs there, the sign can tell us if it's going up or if it's going down. Obviously, here the population went up because we started at 4869, went up to 6375, it went up, and we got a positive sign there. When the population went down, we get a negative sign. It's going to be important concept, well, in the next section, but also in calculus, looking at the different signs of rates of change, telling you something about the function. But in this case, if their average rate of change is positive, the function is getting bigger. The average rate of change is negative, the function is getting smaller. This last two questions, though, we should be able to just look at the table to tell us these answers. It's asking for what period of time is the population going up. Well, just looking at your populations here, 3220 to 3645, it's going up, 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 up until 2012, right? So if we wanted to write that in interval notation again, you would write 2002 to 2012, right? I put brackets. You can put parentheses too. I should probably put parentheses because usually we use parentheses for increasing and decreasing. But here we're just reading it off the graph. And you can tell, again, if you did the average rate of change, if I took the big number, the 6375, minus the smaller number, I would get a positive answer, right? So again, a positive rate of change is telling us that the function was going up. Likewise, if we wanted to do decreasing, what interval would you say it's decreasing? Yeah, 2012 to 2020. I really should put parentheses around those because, again, we don't want to say what's happening right at 2012. So 2020. That's okay? All right. So let's extend this notion to function notation. That's what we're going to do on the next page. Again, remember for our average rate of change, it's the net change in the function divided by the length of the interval that we're talking about. You've already told me that it's where you ended up minus where you started for the net change, right? So if we want the average rate of change, how do you figure out the numerator? How do we figure out the net change again? If I have a function f, how do we figure out the net change? What did we do? Good, f of b minus f of a. That's exactly right, right? We put in the ending point into the function. That tells you where you ended up for your y values. You put in the beginning point into the function. That tells you where your y value started. The difference gives you your net change. How would we figure out what the length of the interval is? What would you do there? What is it? The b minus a, exactly. That's the difference of your x coordinates. You've probably done things with lines before. You're doing kind of a rise over run idea, right? Change in y over change in x. We subtracted y's, we subtracted x's. We're going to talk about linear functions again in the next section. But this is how we figure out average rate of change for a function. So if we want to do this for these examples that we have down here, I want the average rate of change of f of x equals 5x minus 3 from -1 to 4. What do we plug in first? 4. Yeah, we'll do f of 4 minus f of -1 over 4 minus a minus 1. What do we get for f of 4 here? 17? All right, we'll do 5 times 4 minus 3, right? That'll give us 17 for that one. 5 times -1 minus 3 for the other one. 4 minus a minus 1 gives us 5. We get -5 minus 3 gives us -8. So, well, -17 minus a minus 8 over 5. And what does that end up simplifying to? Yeah, 25 over 5, which gives us 5. Literally just plugging in the numbers into the formula and simplifying it. There's not much to it other than that. Might be some interpretation if it's a word problem, but it's actually finding the average rate of change. That's what it is. If I replace the f of x with a y and write it as y equals 5x minus 3, what kind of a function do we have, or what kind of a graph would you have if you had y equals 5x minus 3? That would be a line, right? What's the slope of that line? 5. I can read it right there, right? Notice that your rate of change came from 5. It's also 5, right? Which makes sense, because the slope is the rate of change of the line. Right? So the slope of the line is the rate of change in this case. Are there questions on that at all? Like I said, it's just a matter of plugging it in. So if we do the next one, you tell me how to do it. What would we do first? With the average rate of change of g here, what would we do first? G of 5 minus g of 2 over 5 minus 2. Good. That's just the formula, right? Plugging in the numbers into the function, dividing by the length of the interval. What is g of 5 in this case? 15. So we would have 5 squared is 25 minus 2 times 5 is 10. 25 minus 10 is 15. G of 2 is 0. 2 squared is 4. Minus 2 times 2 is also 4, right? So we get 0. Everybody okay with where the 15 and the 0 came from? Okay. And then we divide it by 3. And again, we would get 5 in this case. Like I said, there's not anything more to it than that if you're actually computing rate of change, right? It's how far you went divided by how long it took. All right. So let's see if we can do a word problem involving these things. This is number 30 in your book in section 2.4, which happens if you have the actual honest to goodness book, it's on page 191. Rather than giving us an explicit definition of a function, they gave us a picture of a function. And it says that the graph shows the population between 1970 and 2020, where they've set x equal to 0 to correspond to 1970. So then x equal to 50 would correspond to 2020. Okay. This one asks for the average rate of change between 20 and 25. What's definitely in the denominator? Let's do that first. What's definitely in the denominator here? 25 minus 20, right? Because that's the difference in the x values, right?
Notice we're not given an explicit function here to figure out the y values. So how are we going to figure out what the y values are? What do we look at? The graph, right? We want to pick off the y values from the graph, right? So if we want
P of 25, what do you get for P of 25? What value is, it's 50, right? Right? On the graph, it's 50. What is P of 20? 40. So we would have 50 minus 40 on top. 10 over 5 gives me 2, right? So that is the average rate of change. What that did not give me, just looking at the formula there, is units, and that's what it's asking for in part B, is kind of the units and interpreting what's going on. It's, remember, it's change in the y value over the change in the x value, right? What units are y in here? What are the units for y? So what's P representing? The population, right? And it's in, notice on the side here it says it's in thousands, right? So when we got a 2 here, that's not really a 2, it's 2,000, right? And the top's in thousands of people, right? Right? What are the time units? Years, right? So this 2 is the fact that the population is, since it's positive or negative, is it going up or going down? Up, right? Is increasing at a rate of 2,000 people per year on average. It's not exactly 2,000 per year at every single moment, but on average, it's 2,000 people per year. That's what I'm saying on average. Again, the reason why it's 2,000 is because they tell us that P is measuring the population in thousands, right? So it's not just a 2, it's 2,000 in this case. The units for your Y's are thousands of people. Questions on that one at all? That okay? All right. This one asks, the last part asks us to identify a period
where the average rate of change is 0.
Well, if I go back up to how my average rate of change is defined, how would you make the average rate of change equal to 0? Well, there better be a horizontal line between the 2 points, right? The points better be the same thing, right? My y values better be equal to each other. So if I look at the graph, do you see 2 points in time where the y values are, I mean, there's lots of examples, but do you see one in particular they're looking for in the pictures by where they put the dots? You see one place in particular where the 2 y values are the same? It looks like here and here they're the same, right? So x equal to 20 would correspond to which year? 1990, and x equal to 40 would correspond to 2010. So the average rate of change is 0 from 1990 to 2010. Bless you. Again, that's not the only time, right? We can see lots of different horizontal lines that intersect the graph a couple of times, right? It's just they gave you those specific dots on the graph where you could see them. Okay. But there's lots of other intervals that would also work. Okay. We just picked that one because the dots were on the graph. But again, the average rate of change is going to be 0 if you see basically a horizontal line, right? Those 2 points are at the exact same height. All right. Any questions on that? Yes.
remember that when you have the graph, the function value is the y-coordinate. So that's where the P of 50 and the P of 40 are coming from. If I look at my graph, your P of, well, I guess it was 25 in this case, but your y-coordinates what give you the value. So here was x equal to 25. So that was where they got the 50 from, because that's the y-coordinate. And the 40 came from the y-coordinate here. Okay. So the y-coordinate on the graph always gives you what the function value is. That's a good question. Yes? Here? Or which one? Okay, so remember that x represents the number of years since 1970. So if we went to 20, that's 20 years past 1970. So that's what gave us 1990. And the other one was 40. So it was going to 2020 or 2010. Sorry, that's where those come from. Okay. Other questions at all on that one? All right. Well, let's do the definition here for difference quotient. We'll save the examples for next time so that you have time to do your quiz here. But when we do the difference quotient, this is an expression of the function where we're basically looking at a slope of something. So let me give you a definition of what the difference quotient is, and then I'll draw a picture here. Okay. So the way the difference quotient is defined as f of a plus h minus f of a all over h. That's our difference quotient. Now, looking at that particular expression, h is some variable, and I'll tell you what that variable means here in a second. H is some variable, but what can't I plug in for h? Looking at the way it's defined, what can't we plug in for h? 0, right? Because we have a fraction, right? I can't put 0 in the denominator, so I need to make sure that my h is not equal to 0. Okay. So how can we think of what this difference quotient means? Well, let's say I just draw a picture of some arbitrary function. So the a plus h piece is representing that we've moved a little bit away from a. How far it is up for debate, but we've moved a little bit from a. All I've done is found the corresponding points that come out when you plug in a and a plus h into the function. If you were to look at, bless you. Oops, why did you do that? I cannot. That's fine. We'll do it that way. If I look at the line between those 2 points this way, can we figure out what the slope of that line is? Don't know why. It won't let me switch my color back. How do you find slope of a line again? Rise over run, right? So I can figure out my slope of that line as f of a plus h minus f of a all over a plus h minus a. What does the denominator simplify to? H. Okay. So this difference quotient we can think of it as a couple of ways, and like I said, we'll do an example of this next time. But we can think of it a couple of ways. This difference quotient gives you the slope of the line between a f of a and
a plus h, f of a plus h.
It's a slope of a line between those 2 points. We actually refer to that as a secant line for the function. It's important in calculus. Okay. But what else does it represent? What did we say earlier that we could think of as slope in terms of functions? Well, how did we start this entire lecture off? It's an average rate of change, right? So you can also think of it as
this is the average rate of change of the function on the interval from a to a plus h, and I'll write that in interval notation. So our difference quotient is giving us an average rate of change. It's giving us a slope. And if you've worked with lines before, you know that slope's an important concept, and it becomes even more and more of an important concept when you go farther and farther along in math. Okay. So like I said, we'll do more examples of we'll do examples of finding difference quotients next time. And we'll also get into the next chapter, next section, I should say. But I want to make sure we have time to do your quiz, so